Welcome to my talk on free and open source silicon, or FOSSi for short. This is a Hitchhiker's Guide. So we starting late, of course, fashionably late. So let's, in mandatory introductory card. So I am a cybersecurity professional, and by night I contribute to ICEDA projects in open source silicon. And so this has led to a few misadventures, such as contributing to HDL21, which is an analog HDL written in Python, as well as being invited to join a IC design competition team, which know a lot more about IC design than I do at Skyworks, and we built a bang-up reference together. So here's my blog, here's my social media. Great. Right. So before I was asked to actually give this talk, when I was preparing for it, Jeffrey asked me a very good question, which is, why would you prefer to do this, making a custom ASIC over just using FPGA for prototyping? And the answer is really the FPGAs are better for prototyping, but ASICs are just more interesting. So we should use those instead. And of course, the main reason that we're interested in open source design as a whole is that we want to lower IP barriers and cost barriers to people who want to develop ASICs, which makes sense. There's benefits for this for R&D. It makes it faster to cycle through R&D, as well as build things out, prototype them, and so on. And also it allows for secure device design, which, they can have a similar effect to hardware as the Linux kernel does to software, where we have a lot of eyes on the same subject. And of course, there is the educational prospects of this stuff. So anyone from the internet can download this and can use this. So that's pretty interesting. So now I've kind of said why. Let's talk about what. So silicon is, the idea of open source silicon is a bit of an oxymoron. As you might have guessed, looking at this diagram, a lot of this stuff you can't download off the internet. It costs tens of millions, sometimes billions of dollars to make any one of these steps. And so no one is making this open source. Not even the open hardware people can make this open source. So when we say open source silicon, we're only talking about this top left-hand corner here, which is the circuit design and the photomask design. So we simulate our circuits and we put them on our chips and we decide what we're actually going to make. So the way that it works in practice is that we have this dynamic that goes between sort of on the left-hand side, FOSS as we know it, so stuff that I make that I put on GitHub that you can download for free. And then on the right, all this EDA doesn't work unless someone actually tells you the physics of what's happening inside of a chip. So you have to contact the people who can actually make chips, and you have to ask them, hey, how do your chips work? And they say, this is how your chips work. So the two work in a collaborative cycle, and they provide something that everyone can eventually use. So on the previous slide, there was this thing called a PDK. So I guess we should talk now about what a PDK is. So PDK is short for Process Development Kit. And this diagram that you see here on the right provides a good graphical summary of what exactly is going on in the PDK. And so you can see that there's like this tower looking thing. So right on the bottom, that's where your silicon is. That's where, depending on how much you know about silicon, that's where your P dopants are going, your N dopants to make N-type and P-type silicon to make semiconductors. But then there's all this other stuff that has to live on top of it to make sure that you can start making the actual components that you want to use, including polyresist, and you can see vias and metal. And so the PDK provides all the data that basically says, how big are these pieces? How close together can they be? How far apart can they be? Is there allowed to be a certain amount of overlap? And because of these constraints, if you fail to follow them, you're not actually going to make a functional chip. So these are all design rules, and they're pretty important. So I actually have a quick demo here, which I just want to show you, which is using a tool called SillyWiz, which comes from Matthew Ben. So I'll just full scale this. And this kind of gives a very good overview of so this is what we're kind of trying to get towards, is this thing here at the end. So you can see as I kind of go through, I have this cross-sectional view, and you can see that there's these different things that are kind of coming off the material, and you can see embedded as well into the material, there's all these shaded regions. So what we're looking at right now is actually, it's an inverter. So that is a PMOS and an NMOS. So see here, this is a PMOS because we have an NWell, and then we have some P diffusion over here, and we have a nice gate in the middle, which is going to create our field effect, which actually makes a MOS. And then because it's an inverter, that's PMOS, so we need an NMOS, and the NMOS lives down here. And then going across the top and the bottom, we have sort of like we have our high digital level and we have our low digital level, so the ground. And so the great thing about SiliWiz is that it is actually, you can actually try whatever you want. It will do arbitrary designs, which you can simulate. And this is actually still an inverter. It's just a very funny looking inverter. So once again, we have all this stuff. And it does also do DRC checks. It isn't an actual PDK, so this isn't actually something that's supported by a manufacturer. But if you just draw like a rectangle across the top of it, you're going to see I got a bunch of DRC errors. So now it's complaining, oh, the poly is going over our transistors. There's diffusion in our contacts. This is nonsense. Get rid of this. So that's good. That means that the DRCs are working. So this is meant to prevent this kind of stuff happening. And this is why we need the PDKs, because this is not obvious unless you own a chip fab. So you can see all my slides there. Okay, so what PDKs do we actually have to work with? So if you think of like a PDK as like a palette of materials that we can paint onto a chip, there's only 2 PDKs that are available right now that the general public can access to make a microchip. The first one was released about 2 years ago, almost to the month, called the Skywater 130 nanometer CMOS process. So the first part refers to a company in America, Skywater Manufacturing. 130 nanometers in this case is the distance between the drain and the source of a MOS. So this is how small your transistors can be. That's 130 nanometers. And then this final acronym right at the end stands for CMOS, which is a complementary metal oxide silicon process. So this the MOS is the same MOS as you find in MOSFET. And complementary in this case means that we have both PMOS and NMOS type things that we can put on the silicon, as we just saw earlier in the inverter demo. And the second process that kind of followed on the heels of this was released by Global Foundries. It's a slightly larger process at 180 nanometers. And the MCU in this case actually stands for microcontroller unit, I believe. So this was originally used by Global Foundries to make microcontrollers. There are a few other PDKs that are sort of, so this is expanding. Like the number of tools that we have available to us is getting bigger. And so there's some of these other ones. I'm going to mention just the first 2, and then there's like some other ones that you can't actually manufacture anything in, but you can use if you're interested in. The first one is a bi-CMOS process. So this is going to be really good for analog processes if you don't want to do something digital that would be completely CMOS. And if you're interested in more modern manufacturing techniques, not everything is like a planar MOS. You also have this FDSOI, which is short for fully depleted silicon oxide insulator, where the gate of the transistor doesn't sit in the plane, but it actually stands up on its edge. So this is how you actually pack more transistors as things get smaller. And this will give you experience with that instead. But both of these things are in preview, so they're still being worked on and are not really like openly supported yet, but they will be soon. And these are the ones, these are the academic ones. So, okay, great. Now we know what an open PDK is. We can start talking about designing some stuff. So this is the basic high-level description of what we do. We start with the spec, so what we would like to do and how much engineering terribleness we're willing to accept. And then we make our way down to the abstraction, where we would implement what we would like the chip to do, either using a hardware description language or a schematic. And then finally, we put it into the realization, which is actually the diagram that we saw before with the polygons. So yeah, so digital design kind of has this workflow to it. So the top half probably looks familiar to anyone that's done any FPGA programming. So we start with an HDL. So for digital design, we're using Verilog in the open source world, and we're using things that are interpreted to Verilog. And then we do a behavioral simulation, so we make sure that the HDL is working as we intended. And then we synthesize this into the actual logic gates that we would like. And then we do some DFT. We wrap it up in some stuff that allows us to do some testing. And then we run the simulation, and we go in this like iterative loop to make sure that the HDL is actually describing what we would like to happen in hardware. And then after this, things start looking less like FPGA programming. They look more like IC design. So we have this floor planning, placement, routing stuff, and post layout simulation. Yeah, and so this is kind of where it gets a little bit more interesting. And so this is what a layout will look like when you're finished with it. Yeah, that is an AES encryption ASIC, which is pretty unusual. And no talk on open source digital design would be complete without talking about the open lane flow. So open lane is well, it's a flow. So it goes from RTL all the way down to right down there, the GDS2 file, which is the actual layout schematic that we want. And along the way, we can see that we kind of go through the pipeline that I described before. And then there's this like green brick in the middle, which has all the other kind of like weird looking chip stuff. So the floor planning, the placement, the clock tree synthesis. And then we wheel over to the top and we have some more kind of like post physical layout checks. So we have to check that things called antenna diodes are inserted correctly and so on and so on and so on. Yeah, so this makes it very easy actually to implement digital designs. You only really need Verilog, and OpenLane is actually quite old insofar as there is now an OpenLane 2, which is written in Python. And I do actually have another demo that I wanted to use for this. So here we go. This might take a little bit of time because we actually have to load in the dependencies. So I'm going to have to return back to the slides. Right. So while it's loading the dependencies, I'm going to talk a little bit about this. So what we can see, and hopefully it's not going to bump us off the screen as we're loading up dependencies, is we have up here a language called DSLX. So this is, it's a language that's interpreted into Verilog that comes from the Google. Oh, there we go. It's running as intended. Yeah, so this is created by the Google open source Silicon people, and it is meant to create a simple enough language for the average user to use. It uses Rust-like syntax, and it gets interpreted down into actual Verilog. So we can see that there's a basic function here where we're going to implement a half adder. So we have two inputs. We want a type 2-bit output, right, consistent with a half adder. And then because it's DSLX, we can just say plus, which, yeah, doesn't make as much sense. But that's fine. So we can, well, we'd eventually be able to run this. So when the dependencies load. Yeah, this takes a hot minute. So we're going to go back here. So while we're waiting for that to load, we're going to take a look at some other stuff here. So it's an open source ecosystem. So that means that we're not just going to be designing things purely in Verilog and then implementing them and putting them into an ASIC and making sure that they work. There's also going to be all these other things that we can put into our designs without having to necessarily reinvent the wheel every single time. So this is like a list of them that I know off the top of my head. But pretty much anything that you can think of probably has been done or is being attempted by someone right now. So this includes, I mean, people have written GPUs, people have written Open RAM, people have written Bitcoin miners, like everything. All that is accessible via GitHub. And so if you go and look into these projects, you'll see that most of the time you often don't have to do a lot of the work yourself. There are people who are out there who've already done most of it. So yeah, let's go back to our demo over here. Make sure it's working. Linking Tara, linking QT. Okay. Looks like we're almost done. Number. Okay. Back once again. The most important one of these is the harness, which is at the top. And this is, yeah. So so whilst we're going to see what the open lane flow produces in just a second, but what it actually produces is just like a rectangle digital design. And it doesn't actually do much of the I/O or any of the kind of the read and write stuff that you need on the bottom of the chip. So if you can see down here, this thing over here is the Caravel harness. And so this has all your I/O in it. It has a couple cells of SRAM. It has a RISC-V core, which allows you to actually talk to your digital design, which is going to be sat on the Caravel harness. All right, let's try this one last time. Okay, great. So this actually works now. So here we can see, and it's going to run some tests, and we get, okay, 0 at 0 is 0. 0 at 1 is 1. 1 at 1 is 2. Okay, so that's good. We've verified that it is working as intended. So now we can now watch it interpret this into Verilog. And so we get some Verilog down here. And then open lane is just a matter of you have to write a config file over here. So we have some parameters that we put in. So okay, where's the Verilog that we're interested in? How big is the chip that we want? How dense do we want it to be? Do we want to be using, do we want a clock port? Probably not. For a half adder, I think will be good. So we just put that in there. We get the JSON file. And here we have our open lane flow. So we just set an environment variable to be equal to the Sky130A PDK. So that just basically tells open lane, I want to be doing this in Sky130, please. So I want to be using the Skywater 130 nanometer process. And then we have a tickle file. And then here, we're actually only going to run the synthesis. So this is the first step where we go from our Verilog to our RTL. And then we have some nice Python graphics, which kind of demonstrate for us what we expect a half adder to be. If you've seen a half adder before, this will be pretty familiar. So we have 2 wires running into an XOR cell, 2 wires running into an AND cell. One gives you the first digit, the other one gives you the second digit. That's a half adder. Great. So now we can ask OpenLane to do the really cool part, which is throw together a chip design for us using a half adder. So this doesn't actually take too long. And you can see as it's going through, it's floor planning. Okay, where's the IO going to go? Where's the power going to go? So on and so on and so on. Global random placement. I'm kind of running off the screen here. Almost done, promise. That thing up there, the black box warning is actually going to throw an error here. So, yeah, that's not good. That basically, that error there is telling us that something called the layout versus schematic isn't working. For us, that doesn't really matter. We don't have to care about the layout versus schematic because we're not actually going to make this thing, for starters. And for a second, we actually already have the layout that's being produced. So the computer has figured out on its own where does the inputs go. So we have the input over here, one input, we have an input over here, we have an output over here, we have an output over here. And it's now assembled using standard cells from the Sky130 OpenPDK, a chip. And so that's a half adder. Okay, great. So you can do more exotic designs, as you saw over here. I think this one was also produced with the OpenLane flow, but the Verilog behind it, of course, is much more complicated. If you want to do AES encryption or any of the other interesting applications that people do. And then, of course, all of these can also fit around an OpenLane flow. So if you want a RAM cell, there's a library for that. If you want an FPGA, you can do that as well. Okay. So at this part of the talk, I was going to talk a little bit more about, so we've kind of seen this like digital flow. So the OpenLane is probably the most important part of this because it lets us build out really big things, but there's also like there's another side to this, which is also the schematic editing, which is more important to doing analog workflows. So now I can just quickly show that to you, and we're going to take a look at a schematic using another open source tool called Xscheme, and this is made by a guy called Stefan Schippers, who is working quite closely on this. And so you can see, so this is actually, so before we were working in the Sky130 process, now we're working in the GF180 MCU process again. And we can see, okay, we have all these various cells that are available to us. So these are standard devices that are also defined in the PDK. And so, yeah, that's what this interface looks like. So we have a symbol here over here for an NFET. We have our simulator code. So if you are familiar with Spice, you will have seen this. And in Spice, we have, yeah, we've written all of our connections that we would like to see. And we also have this part over here, which tells us what we're going to do to the voltage. So we're going to step it. And then we got another voltage here for the ground that we're also going to step. And then a part of Xscheme means that you also have to include, these things. And there's a process to include these as well. So you're interacting with like a library of Spice files, and then out of the Spice files comes the actual design of the transistor. So Xscheme makes it very easy for you to draw a schematic, and then you can just run the netlist here. these warning signs are actually not going to be a problem. And then we can ask it to simulate it for us. He said, there we go. Okay, so ngSpice is our simulator of choice. It is old. It is older than Linux old. It's descended originally from the Spice 3.5 project. So yeah, it is very, very old. So here we've run our simulation at a temperature of 27 degrees. We now have a raw file, which is storing all of our simulation data. And so the nice thing about Xscheme is that we can plot it inside of Xscheme. So we can do this by pressing Control and clicking. And then you can see that this is the kind of behavior that we would expect as we vary the voltage across a transistor, right? So we have varying currents going across our drain. So yeah, everything's working as intended. And yeah. So this is Xscheme. There's another, so this isn't the only simulator that's actually interactive with this. There's another one called Zeiss, which does this in parallel, which is a little bit faster. But yeah, you probably want to be using ngSpice. Zeiss is not easy to use. So, all right. I also want to show you another tool. So this is called K-Layout, and it is another program that is used for layout. So we saw the SiliWiz thing, which is great, but it doesn't actually do real layout. So here we can just quickly throw together some kind of design, right? And so we have all these tools that we can use. And so we can just take a look at some of the things that we want. So we can go down here, we can look for our cells, right? So say that we want a BJT or a PFET or an NFET. And we can just quickly put together one of these by checking across here. And we can, so we have these things in the PDK called parametric cells, which mean that you don't have to manually draw out the polygons every single time. You can actually you can make sure that all of these things work together as you need them to. And we get this material that we need to actually define the thing that we want to define. So here we have a very small NFET. And so we can just put that down here. And that gives us a nice little rectangle that we have on the screen. And then we move up a layer, and then we can see the individual materials that are now drawn. So this is using the GF180 PDK. So we have various materials, and we can focus on just the layers that we have of interest. So we have on the right, we can see that when it's yellow, it's a metal layer. So it's like an interconnect layer. We have the contacts, which are going to contact between the metal layers and the silicon. We have these other materials here, which are for N-doped and P-doped silicon. And yeah, so now we can, yeah, that's a parametric cell. So if we wanted to make another parametric cell, we could recreate the design that we just saw earlier. And we could take a look at a PFET. So PFET, by default, has to have a width that's about, if you want to be making some consistent design decisions, PMOSs are about, yeah, they work at about half the rate as an MMOS. So you have to have them twice as wide. And so I can just place that down here, I believe. And yes, so you can just move these things around. So on and so on and so on. So move. And so on, yeah. And I can move things. Great. And if I wanted to, I could go through the entire process of drawing an inverter, and then we could see the DRC checks and the LES, but I think you get the point. So, right, where were we? Here's a ring oscillator in Xscheme. So let's assume that you came away from this and you felt that you wanted to actually make a chip. So what is actually available to us in terms of options for everyday people without access to a company like Apple or TSMC. There's only really one company that's available for most of us, and that's eFabless, who are able to take these designs and push them into open PDKs. They will do, if you have a need for an ASIC and you want to produce 1,000 of them, that will be $10,000. But that is beyond the reach of probably most students and people who just want to do this on the side, like myself. So what comes next is these multi-project wafers and free shuttles. So Google works with eFabless, and it provides these free shuttles where you can basically upload these designs that you would like to actually put on a wafer. And instead of having, so what normally happens is that on a circular silicon wafer, you have all the design, you have one design, and of course you want to mass manufacture it. So you fill out the entire wafer with what you want to print. But what we need for students, for people that want to just do a quick prototype, is we need an individual wafer, die in the wafer for every single contributor. And so this is made available through multi-project wafers. Usually, though, to design your own microchip, that it would require a team, and you'd have to be working on that for a very long time. So what is really the most available to people who are just interested in doing this as like an educational thing or as a hacking thing is what I have kind of like dubbed here multi-project wafers, which is instead of dividing up the wafer into multiple dies that each containing a project, you now actually split up the die itself into lots of little areas where you can put tiny little projects. And so this is the basis of one very popular thing that's available right now in these open source PDKs called Tiny Tapeout, where you can submit a small design and have it wired up into a chip, into a harness by Matthew Venn. But all the tools that are necessary to actually wire up designs are open source. So if you wanted to run one of these things yourself as either an organizer of a class, then yeah, that is another thing that's available to you. And so here I've just left a big old list of things that you can go look at if this is something that is of interest to you. The number one thing at the top is what I recommend the most if you are doing this for the first time, because it loads practically all the tools that I've talked about here and much more that I didn't have time to fit in. It's a Docker container as well, which means that you can it doesn't matter what operating system you have. Most of the tools that I'm discussing have only been developed for Linux. So if you would prefer to do it in Windows or you would prefer to use Mac, there's going to be a problem there. And so the Docker really simplifies that. It gets around like all of this, the build issues. And I mean, the demos that I had, as slick as they were, actually took hours of time to figure out, what build flags do I need to use, what needs to be hooked up. So Harold Predel's Docker makes that really, really quick and easy to do. The next one is a course. There's a course available that you can do Tiny Tapeout. If you would like to go do that, called Zero to ASIC. And then, yeah, I got some design competitions here. So these are design competitions that are ongoing at the moment. Pico is a pretty interesting one where people are designing an analog harness, which includes like an oscilloscope on the chip that you can use to do analog designs, which is something that's still not really happening right now in open source. And then, of course, there's these other these two organizations here, the Chip Alliance and FOSSi Foundation, are definitely worth reaching out to and attending one of their talks. Look into their webinars. They have a lot of cool stuff. And there's also Google Silicon, which is well worth a visit. It provides a lot more of these kind of like cloud-based notebooks that I showed you, where you can go through and you can actually see, and it'll teach you a lot more than I'm able to here today. And then, of course, there are also a lot of people on YouTube that are actually producing tutorial content that actually shows you and steps you through how to use these things and to build out systems using these open PDKs. And then, of course, last but not least, probably the most important thing is that all the community is actually on a single Slack server, which is right at the bottom, which you can go access if you want to make some chips. So, yeah, and then I think I have most of these again on the same slide. So I'd say that's the end of my talk. I'd like to open the floor to any questions that anyone might have.